Okay, so is everyone able to see this?
Yes.
Can you all see my cursor also? Can you see my cursor? Yeah, okay, great. All right, well, it's a pleasure to finally give this colloquium, even though it is unfortunately still remote, but it's still nice to be able to do some kind of semblance of the real thing. And I've been very excited to give talks on this subject in general because we're in a very exciting period regarding the black hole information paradox. And I called it in the age of holographic entanglement entropy because I think this really ushered in a new era of what we can do and what we can learn about quantum gravity from the black hole information paradox. So I want to begin with a slight step back and some motivation, why we study these things, why we study the black hole information paradox, and from there I'll move on to what the paradox really is and how holographic entanglement entropy can help us understand it better and work towards a resolution. So a few things that we know. A lot of this talk will be about what we don't know. So let's begin with what we know. Well, we know that general relativity is not a complete theory of gravitational phenomena. General relativity sort of predicts its own downfall. It predicts its own end of evolution by predicting singularities. And singularities are regions where relativity simply breaks down. Our traditional picture of gravity breaks down. These are regions of extremely high curvature on very, very small scales. So for example, deep inside black holes, in the pre-inflationary universe, this is where we don't expect general relativity to give us a good description. And what we really need is a theory that can describe very large curvatures on very small scales. In other words, a quantum theory of gravity. And so in general, our universe is pretty well described by a decoupled limit of general relativity and quantum field theory. We don't normally have to consider fully strong, non-perturbative quantum gravity to describe our universe. But in these regimes where we're talking about deep inside black holes, the pre-inflationary universe, these are regimes where quantum theory of gravity is necessary. Now, we would love to describe the pre-inflationary universe, the Big Bang, the deep interior of black holes, but we don't have a self-consistent, direct, non-perturbative formulation of quantum gravity. Emphasis on direct, we do have some indirect formulations. So this is what we know. We don't have this thing. We would like to have it. Now, one place where we can focus our investigations is black holes, essentially as a laboratory for thought experiments. So here is a quote from Franz Cordova. Black holes are the most mysterious objects in the universe. And this is a picture of a black hole coalescence. And so one thing that we don't know, and we would really like to understand, is the black hole interior. Now, it's of course understandable that we don't understand the deep black hole interior, because as I said, that's where we expect very strong gravitational effects on very small scales. We need non-perturbative quantum gravity. Now, what is the role of the information paradox in all of this? Why do I bring up these things that we need non-perturbative quantum gravity for in a talk that's intended to be about the black hole information paradox? And the answer is rather surprising. Even though we don't expect that we need non-perturbative quantum gravity to describe the, say, near event horizon region of a black hole, it turns out that maybe we do. So what happens with the black hole information paradox is a problem that occurs when we try to apply semiclassical gravity and quantum field theory in the same place in a regime of space-time where we expect that both should be valid. In a regime of space-time where curvatures are small and we don't expect non-perturbative quantum gravity to kick in. And that is why this black hole information paradox is a paradox rather than just, oh, something that we don't understand yet, like the black hole, the deep black hole interior. Because we expect that semiclassical gravity is valid in these regions. And when we just use semiclassical gravity, up until very recently, when we use it, we get answers that are not consistent with what we expect with what we think we know about quantum mechanics. So now I'm finally arrived at the information paradox. What is it? Why do we care about it? So the information paradox is an apparent contradiction between the predictions of semiclassical gravity, essentially at the event horizon of a black hole, and unitarity of quantum mechanics. So we expect semiclassical gravity to be valid at the event horizon of a large black hole. We don't expect that there are any large curvatures there. We also expect that quantum mechanics is unitary. And these two appear to be contradicting one another. That is essentially the statement of the information paradox. So the caricature that you'll often hear, how people characterize the black hole information paradox, if they sort of have to do it in an elevator, is they say you have two observers that are entangled, Alice and Bob. Alice ends up inside the black hole, and Bob doesn't end up inside the black hole. Then the black hole evaporates. And so what happens is we started out, we had Alice and Bob were entangled with one another, but they were in a pure state together. And once the black hole has evaporated, taking Alice with it, Bob is left in a mixed state. And so what happened there, and I'll go over this in more detail later, but what happened essentially is that a pure state evolved into a mixed state. And that is a violation of unitarity. So this is the sort of setup of the paradox, and I'll say much more in detail about what this is and what it means. But that's the what. How about the why? The why is that this is a paradox, and nature doesn't really do paradoxes. Nature works, something happens, and if we have a paradox, it's our failure to give an accurate description of what is actually happening. And so what this information paradox has to tell us is that we're thinking about things wrong. There's something that we misunderstood, some piece in the framework that's missing. And so the hope is that if we can understand the information paradox better, if we can resolve it, then we would learn a lot about quantum gravity. Because the reason that we have a paradox in the first place is some misunderstanding that we have, some fundamental basic misunderstanding about quantum gravity. There's a bit of a potential catch-22, of course, which is, can we get insight into the black hole information paradox without having a direct formulation of non-perturbative quantum gravity? And the exciting thing that I can tell you now is that, yes, we can. And that is essentially the content of this talk. So the outline, oh, not quite yet, okay. Outline in a little bit, let me finish the introduction first. So a little bit more about the information paradox and how it's changed over the years, and also what's different now in this past year and a half of the very rapid development versus before. So historically, like many other areas of physics, the black hole information paradox, it sort of has this history of very long periods of relative silence and very short periods of frantic activity. And at the very least in my field, I would say the black hole information paradox has more silent, the silent periods are more silent and the frantic activity is more frantic. It's more like a series of delta functions. But I think that the current developments really are a little bit different. So before 2019, so before mid-2019, when there were the two discoveries that kind of catalyzed this, the general perspective, what we thought was that unitarity and black hole evaporation, and unitarity here means conservation of information. In the sort of information paradox, information conservation refers to unitary evolution. What was thought is that unitarity and black hole evaporation is going to require some non-perturbative quantum gravity calculations. And that no matter what we do in semiclassical gravity, we're just going to see information loss. There's nothing we can do in semiclassical gravity that's going to give us evidence of unitarity. And of course, this is very confusing because we don't understand why that is and why semiclassical gravity is getting things so wrong in a regime where it should be valid. And what the recent new results are is that essentially what catalyzed all of the recent developments of the past year and a half is a purely semiclassical analysis that is carrying a hallmark of information conservation or unitarity. So it's purely semiclassical and it's extremely exciting. And I really think it's safe to say that the vast majority of us thought that this was probably impossible, that we really were expecting that we would have needed non-perturbative quantum gravity to see something like this. So that's been tremendously exciting and one of the reasons that I'm very happy to be giving this talk. And also what has been, what the expectation that has been borne out is that learning more about the black hole information paradox really has taught us more about gravity. And so this last bit of this talk will be understanding how this discovery, this purely semiclassical analysis that showed us evidence of unitarity, how it's taught us more about quantum gravity than just the calculation itself. So with that, let me give an outline of the talk. So I'll spend a little bit of time talking about the information paradox before these new developments, essentially the setup of the paradox, what its statement is, and where we were going with it. Then I'll spend a little bit of time talking about the new tools. So the tools, holographic entanglement entropy, are critical for us to be able to do this semiclassical analysis that gives us signatures of unitarity. And then I'll pull it all together into what has been happening since May 2019 when these results first came out. And I'll even be a little more audacious and speculate on what I think we'll be seeing in the coming years. So with that, let me begin with the background on the information paradox. And I will begin, as things in physics often do, with thermodynamics. So it is a fact in general relativity, or you could debate whether it's a fact or not, but generally understood perspective, that black holes have no microstates. If you specify the charges of a black hole, mass, charge, angular momentum, that's basically all there is to it. So this is a very famous experiment, Wheeler's teacup experiment at Gedankenexperiment, where you take a hot cup of tea and you throw it into a black hole. Now, a black hole has no entropy since it has no microstates. So if you take a hot cup of tea, which certainly has entropy, and you throw it into the black hole, then it appears that you have decreased the entropy of the black hole. And you can, of course, maybe with a single teacup, you're not that bothered, but you could take entire galaxies, throw them in and dramatically decrease the entropy of the universe. Now, one of my favorite quotes by physicists is by Sir Arthur Eddington, which is, if your theory is found to be against the second law of thermodynamics, I can give you no hope. There is nothing for it but to collapse in deepest humiliation. And so here we have this beautiful theory of general relativity, and unfortunately, it appears to be collapsing in deepest humiliation. So Wheeler was very upset by this, and he went to his graduate student, Jacob Bekenstein, and told him, find a way to solve this. And whenever I think about that, I think I'm being a little too easy on my graduate students. So what did Jacob Bekenstein do? Well, he rose up to the challenge, and he said, okay, black holes are thermal objects. They have a temperature, and they do have an entropy. And yes, maybe they don't have microstates in general relativity, but they have microstates in quantum gravity. This thermodynamic entropy is a result of quantum gravity microstates. And we compute it in the following way. It is the area of the event horizon over 4gh bar. So this is known as the Bekenstein-Hawking entropy due to Hawking's contributions to this. And indeed, this was borne out by calculations by Hawking, who in fact set out to show that this was false and ended up finding the opposite. So for a black hole close to equilibrium, we can compute a temperature, and we find that it's inversely proportional to its mass. Now, I want to emphasize here that it's very important that there be quantum corrections. I already said that classical black holes in general relativity don't have microstates, but it's also true that classical black holes in general relativity are perfect absorbers. So they wouldn't have a temperature, because for that they'd need to emit radiation. So I want to emphasize it's very important that we're including quantum corrections here, that we're not working in classical gravity, but in semi-classical gravity, which means that we're working in this regime where we have classical gravity and it very weakly interacts with the quantum fields in the space-time. So this is more of an aside, but I just want to emphasize that for the black hole to genuinely have a temperature, you have to take into account quantum effects. So now let's talk about evaporating black holes. So black holes are thermal. That means they should radiate. And if the temperature of a black hole is hotter than its ambient surroundings, then as it radiates, it should shrink, losing mass. That means evaporate. But since the temperature is inversely proportional to the mass, then as the black hole evaporates, it gets hotter, and it keeps on evaporating until it's completely gone. Now, why don't we see black holes exploding, evaporating all over the sky? Well, the numbers don't really work in our favor. We'd love to see, speaking as someone who works on quantum gravity, I'd love to see evidence of evaporating black holes, but the numbers are not in our favor on this. So for example, Sagittarius A star, current estimates of its size give us a temperature, a Hawking temperature of about 10 to the minus 14 Kelvin. So that is certainly not going to evaporate in our universe. Now, a solar mass black hole has a temperature of about 10 to the minus 8 Kelvin. And a lunar mass black hole will have a temperature that is going to be at equilibrium with a cosmic microwave background. And just for kicks, a coronavirus-sized black hole will have a temperature which is at room temperature. And I'm sure there are conspiracy theorists out there who would love to know this information. So here are the numbers. And now let's ask, all right, so what's the problem with evaporating black holes? Why do we talk about them in the context of the information paradox? So before we talk about that, I actually want to use some diagrams to illustrate what happens for collapsing black holes, which we'll then use to illustrate what happens in evaporating black holes, which will be very useful for tracking down what goes on when we talk about the information paradox, especially in the context of holographic entanglement entropy. So let's, this picture, what it's meant to do is it's meant to show you a star. So this thing over here is a star. I know it doesn't look much like a star, but this, you should think of this as a sphere. I have squashed all the spatial directions so I can draw the time direction well. So suppose this thing is collapsing under the force of its own gravitational field. And, oh, sorry, wrong direction. So the radius of this thing is shrinking as we roll forwards in time. Again, time runs up in this direction. And as it shrinks past its Schwarzschild radius, we get an event horizon forming. So this gray sphere, this gray surface over here, the cylinder is meant to be the event horizon. And eventually the black hole keeps on collapsing and eventually it forms a singularity. So this is sort of what's called an Eddington-Finkelstein style diagram of the structure of black hole collapse. So this, again, this jagged line over here, hope you can see it, a little faded. This is the singularity. So just to have a bit of a clearer picture of what is happening here as far as where light rays are going. So if you're standing out here far from the black hole at this point, and you're holding a flashlight and shining that flashlight, this is the light cone of those rays of light. What that means is this is how light rays are traveling. You can travel everywhere inside the light cone. That's the space of everything that travels less fast than light. And outside the light cone is the area of space like separated to you, meaning you'd have to travel faster than light to get there. So essentially, this is your future, everything inside this light cone. Now, the effect of space-time being curved and the event horizon is that these light cones essentially start to tip, so that this eventually, when you reach the event horizon, the light cone is tipped so that all of the interior is facing towards the black hole. And the deeper in you get, the more they tilt. And essentially what happens is the singularity is part of your future. So it's unavoidable. So this is the basic causal structure of a black hole. Again, so far we've only talked about collapse. Now, what about evaporating black holes? So what happens for evaporating black holes? Well, the area of the black hole shrinks, the event horizon shrinks, until eventually it gets down to some quantum gravity mess over here, potentially some explosion. And these two are meant to be the trajectories of Alice and Bob, which is of course an idealization, but we think about a bell pair, for example. One of the particles falls into the black hole, the other one stays outside of the black hole. Now the paradox, again, is what appears to be information loss between the initial state and the post-evaporation state. And in order to see this in a very clear way, it's very useful to talk about the entropy of the Hawking radiation. So the entropy of the stuff that ends up outside of the black hole. So let's talk about that. So in a very dramatically oversimplified model, but it still kind of gives a basic idea of what's going on, we take an entangled pair where, say, the left particle, Alice, falls into the black hole, and the right particle stays outside of it. So this is a bell pair. I can write the state of the two particles together in this way. Now, if I want to ignore the left particle and consider only the state of the right particle, I trace out the appropriate degrees of freedom, and I end up with a density matrix. This is a maximally mixed density matrix. I can't represent this as a vector in a Hilbert space. This is not a pure state. All right. Well, we want to track the entropy of this radiation. Like I said before, that's something that's going to make it very easy for us to diagnose information loss. So how do we do that? Well, we'd use the von Neumann entropy, also known as the entanglement entropy or the fine-grained entropy, which is defined as minus trace of rho log rho. Why do we like this quantity? Well, for one, it's invariant under unitary evolution. It also vanishes for a pure state and only for a pure state. And finally, it's bounded from above by the thermal entropy, also called the coarse-grained entropy. So these are three properties of this object that we use to diagnose whether the system is evolving unitarily or non-unitarily. So let's talk a little bit about information loss. Why do we call it that? What does that mean? So a very, very rough intuition is that we can quantify in a rough way the information in a state in terms of the difference between the thermal entropy and the von Neumann entropy. So this is something we can roughly think of the amount of information that a state has, essentially because the thermal state is so coarse-grained that you don't really know anything if you have it. So the thermal state, again, is at equilibrium. It essentially has no information. So if a system starts out at some value of the von Neumann entropy, and it evolves to progressively larger values of the von Neumann entropy, then it gets progressively closer to S thermal, and the difference between these two shrinks. So we say that information is lost. Now, alternatively, we can think of a pure state as the entire system. So in other words, if we have a mixed state, we can always add stuff to it to make it pure. So if we think of a pure state as an entire system, then the von Neumann entropy tells us how short we are of having the full system. So if the von Neumann entropy is only 0 for a pure state, so if it's some non-zero value, then we're missing part of the system. This is a basic intuition behind why we call this information conservation or information loss.
Sorry, Netta, one
Yes.
thing, you said correctly, right, that the von Neumann entropy is invariant under unitary evolution. So right. If it grows, it means that the evolution is non-unitary. Right.
So I think I know what you're about to say, and I think I'm about to address it. So this happens all the time, right? We have an open system which will interact with its surroundings, and its entropy will grow. And it doesn't mean that the entropy of the universe is not, that the state of the universe is not evolving unitarily, because we're talking about a subsystem. So if we're talking about an open system, then of course it can evolve. There's some time-dependent Hamiltonian things can evolve non-unitarily, that's fine. Open systems don't have to evolve unitarily. The point is that closed systems do, and the entire universe is not an open system. And we expect that the entire universe should not lose information. We should not begin with having all the information about the universe and then eventually somehow end up being short of having the full system, even though we still have access to the full universe. So that's the rough intuition of why we would like the entire universe to evolve unitarily, and it's a problem if it doesn't. There is another problem with it, which is that, of course, in physics, we like to be able to predict as well as post-dict. And if we end up with a mixed state after the black hole evaporates, or if in general, if we end up with the entire system ends up with a mixed state, well, we are not going to be able to evolve that back in order to figure out what the original pure state was in a deterministic way. So it would appear that we have lost determinism along the way if we allow ourselves to have this evolution from a pure state to a mixed state. So let's talk about the Hawking radiation now. In the very simplistic model of the Bell pair, the initial state of the pair is pure. This is a single, this is vector psi, the state of the pair is pure. Now, after the black hole has finished evaporating, one of the particles is gone. So we take the state of the pair, it's just the state of the remaining particle, which is a mixed state. And its entropy is log 2, which of course is not 0. So that means that the entropy has increased and the system was not evolving unitarily. So what was Hawking's calculation? Well, the basic idea is the following. We form a black hole from a pure state. So we take a bunch of stuff, all of this matter is in a pure state, and this pure state forms a black hole. And we want to compute the entropy of the radiation. What does that mean? That means the entropy of quantum fields that live outside of the black hole. So initially, before the black hole starts to evaporate, this entropy is 0. So everything is 0, we have a pure state. Now, as the black hole starts to evaporate, the entropy of everything outside of the black hole starts to increase. So that's this over here. Why does it start to increase? Well, because now we have two systems. We have the black hole interior and we have the radiation. Neither one of these is a closed system, so it's okay that the entropy of one of them increases. Now the black hole then continues to evaporate, and we keep on having these bell pairs where one of them goes into the black hole and the other makes it out to infinity. So the entropy keeps on growing and growing. And then eventually, what ends up happening is that the black hole finishes evaporating and we saturate the entropy at some thermal value. The end state is not pure. So the universe evolves from a pure state over here to a mixed state. And this is, to be clear, the entropy of everything that remains in the universe, because there's no longer a black hole interior, since now we're talking about everything in the universe, which is just the Hawking radiation. So we've lost information. Now, okay, what have we found? We found that the pure state in a closed system evolves to a mixed state, and information appears to be lost. So what's going on? Is quantum gravity actually non-unitary? Maybe there are some non-perturbative corrections that somehow fix this. What would a unitary entropy curve look like? So Page did an analysis where he computed what a unitary entropy curve would look like. And essentially, this is what it has to do, although I've certainly removed many different small qualitative features. So why does this curve look the way that it does? Well, as we said before, initially, the entropy has to grow since we had one system and now we have two and they're interacting. But once the black hole has evaporated half its mass, then what ends up happening is that the Hawking radiation now contains more than half the system. And so we expect that it should begin to purify itself, that as the entropy should start going down, because if the evolution is unitary, then as the black hole continues to evaporate, the Hawking radiation somehow knows more and more. Because at the end of the day, if this is unitary evaporation, then information should somehow escape. And as we gain more and more information about the early radiation, this entropy goes down. And eventually, we expect that once the black hole finishes evaporating, the Hawking radiation is completely in a pure state, so that the entropy before and the entropy after, the entropy at the beginning and at the end, is the same. This is what unitary evaporation would look like. Now, which is the correct curve for quantum gravity? Is it this one or is it that one? And how can we calculate it? How can we actually calculate the Page curve? And that brings me to the age of holographic entanglement entropy. And what we're going to do is we're actually going to calculate the unitary Page curve for using just semiclassical gravity. So a preview. From the perspective of semiclassical gravity, it's really hard to see where Hawking's analysis went wrong. And it would seem that we need an ingredient from quantum gravity that would help us figure this out, figure out where was the mistake. Now, what was found in the new developments is that a completely semiclassical calculation can actually give us this unitary Page curve that goes up and comes down, but only if we use the correct interpretation of that calculation. And that interpretation is inherited from quantum gravity. And in particular, when I say quantum gravity, I mean quantum gravity in the form of holography or the ADS-CFT correspondence. So let me say a few words about the ADS-CFT correspondence. For quantum gravity with ADS boundary conditions, which we often call the bulk, is dual to a lower dimensional non-gravitational quantum field theory that we call the boundary. That is, the statement of the ADS-CFT correspondence, or the conjecture, if you like, is not proven. But it's very well tested, and it's a very powerful duality because it is essentially a statement about quantum gravity. We normally work in the limit where quantum gravity is semi-classical gravity in anti-de Sitter space. But we don't have to do that. In general, the statement is supposed to be a conjecture about quantum gravity with anti-de Sitter boundary conditions in general, so including non-perturbative quantum gravity. Now, just a bit of intuition, when I say anti-de Sitter space, this is essentially like a box, quantum gravity in a box, effectively, an infinite box. Now, one of the powerful statements that ADS-CFT makes for us is that a black hole is just another quantum system. So if we have a quantum field theory, a conformal field theory, really, a CFT, which is dual to quantum gravity with ADS boundary conditions, then that means that a black hole in anti-de Sitter space is just some state of an ordinary non-gravitational quantum field theory. And there's this beautiful picture from a program from a few years ago on ADS holography and the quark gluon plasma. So now we can say, all right, well, quantum field theory evolves unitarily. That's this thing that we think of as on the boundary of this soup can. So quantum field theory evolves unitarily. And doesn't that immediately imply that quantum black holes must also evolve unitarily? I mean, this is a duality, right? We have a black hole inside, and it's dual to a state in a quantum field theory, which evolves unitarily. So haven't we solved the information paradox? We now know that black holes evolve unitarily. Well, yes, but it's not really satisfactory in the sense that we want to understand how this happens. We want to understand what is the gravitational mechanism that allows the information to escape. So can ADS CFT help us out with this, or is it just giving us some top-down description, some very broad statement, it's unitary, now that's it, that's all I'm going to tell you? Is it giving us more details? And the answer is yes. And here is well, I can tell you what the basic idea is, and then I'll talk about holographic entanglement entropy. So we already know that if we compute the entropy of the bulk, the quantum gravity in ADS, by the usual formula, so minus trace rho bulk, log rho bulk, then we get the Hawking curve. We can find that information is lost. So let me just explain this picture here. We begin at early times so we form the black hole from some quantum state rho bulk, which is pure. So this is rho bulk of before. Then sometime in the middle, we evaluate the entropy again. This is the entropy outside of the event horizon, so rho bulk T during. And then later we evaluate the entropy, for a state after the evaporation. And what we find that this is non-unitary, so that the entropy of this is 0 and the entropy of that is not. Now, meanwhile, on the back of the soup can, so in the boundary theory, what do? Well, we say, okay, here's the boundary state before, during, and after. And in the CFT, it's all kind of boring. It just evolves unitarily from here to here to here. So if we compute the entropy in the CFT by the usual formula, we just get a unitary result. All right, now what? Well, the idea is that we want to compute the entropy of the CFT, but what we're going to do is use the semiclassical bulk to do it. And how are we going to do that? We're going to use the holographic dictionary that relates entropy on the boundary to gravitational geometric quantities in the bulk. That mapping is what's going to allow us to compute a unitary entropy evolution from gravitational quantities. So this is what we could call a holographic calculation of the entropy. So we're going to calculate the entropy of the CFT using quantum gravity or semiclassical gravity. And remarkably, when we do that, we actually get a unitary page curve. So we use geometric and gravitational quantities to compute a unitary page curve. So let's talk about how that works. And the important ingredient here, of course, is how do we compute entropy of the CFT using quantities in the gravitational theory. Now, if we're just working in general relativity and we forget all about quantum fields and we don't worry about the effects of those quantum fields, then we have the celebrated Ryu-Takayanagi proposal. And the Ryu-Takayanagi proposal tells us that the von Neumann entropy of a boundary state is given by the area of a certain distinguished surface in the bulk over 4gh bar. So this certain distinguished surface has to satisfy a number of requirements. I won't really talk much about those requirements except for one of them, which is that this surface is what we call an extremal surface. What does that mean? It means that if you take this surface and you wiggle around its location a little bit, this area doesn't change to first order in those perturbations. So the first order perturbations of this location don't change its area. It's an extremum of the area functional. And if you have multiple such surfaces, then this is the minimal area surface between all of them. For example, for a stationary black hole, the extremal surface that computes this entropy lies on the event horizon. And that is basically the same as the Bekenstein-Hawking formula that tells you that the entropy of a black hole is equal to the area of the event horizon over 4G bar. Now, this story is a bit more complicated for non-stationary black holes, but it gives the general idea. Okay, well, that's great. We have a way of computing the entropy if we have purely classical bulk. But a while ago, I mentioned that if we're talking about purely classical general relativity, then black holes are not really thermal objects, right? They're perfect absorbers. They don't have a temperature. They're not going to evaporate in classical general relativity. So that means that this formula, while it's nice, it's not enough. We need to include quantum effects in the bulk. How do we do that? Well, we can include quantum effects to first order, meaning just quantum fields propagating on our curved background, but without worrying about how these quantum fields interact with the geometry. So how do we compute the entropy in that regime, the so-called quantum field theory on curved background regime? Well, this was by Faulkner, Lukowitz, and Maldacena, and their prescription was the following. They said, you take the area of the same surface as before, this extremal surface X, and over 4G bar, so that's this X here, and you add to it the von Neumann entropy of the quantum fields outside of it. So if this is a spatial slice of the space-time, this row out of X is the state of the quantum fields that live outside of X, between X and the asymptotic boundary. This quantity here is called this generalized entropy of this surface X. So what Faulkner, Lukowitz, and Maldacena said is the von Neumann entropy of the CFT is given by this generalized entropy of this extremal surface X. That's great, but we actually want these quantum fields to actually interact with the metric. Otherwise, the black hole is not going to evaporate. For it to evaporate, it actually has to shrink. The geometry has to change as a consequence of what these quantum fields are doing. So what we actually want is to work at higher order. We want to include quantum corrections due to the interaction between the metric and these quantum fields. And the way we do this is we actually use a very similar formula, but what we have to do is we have to modify the surface. So once again, we compute the generalized entropy, but this surface chi is different. Before, we had a surface that extremized the area. If you wiggle it slightly, its area doesn't change. This one, if you wiggle it slightly, this whole quantity doesn't change. So it is an extremum of this entire quantity, the so-called generalized entropy. And once more, here's a picture. Here's a quantum extremal surface, is what we call them. And this here is the state of the quantum fields outside of it. But this surface is different from the red one from before, in the sense that this is the local extremum of this whole quantity, rather than of just the area. So the difference between these quantum extremal surfaces and just the ordinary ones is that you're extremizing a quantity that includes the von Neumann entropy. All right, so these are the tools, essentially. And now that we have the tools, we can finally get to the fun part of saying, all right, so what did we actually do that computed a unitary page curve using purely these semiclassical techniques? All right, so let's consider an evaporating black hole in ADS. Now, immediately there, you have to stop and say, well, actually, ADS black holes don't evaporate, so we have a bit of a problem. Part of the reason ADS black holes don't evaporate is because you can say the radiation, if they're large, the radiation essentially bounces off the asymptotic boundary. Remember, it's like a box, comes back to the black hole, and the black hole reaches equilibrium with the radiation. So small black holes do evaporate, but as it turns out, we don't understand them very well from the perspective of the ADS-CFT correspondence. So we have a bit of a conservation of misery situation here, but what we can do, and what we did, is we forced a large ADS black hole to evaporate, essentially by extracting the Hawking radiation by hand. So not allowing it to just bounce off the asymptotic boundary and come back. And the way that we did this was by essentially attaching a cold bath to the box boundary at infinity. So here is, we have this, this bulk, that's the gravitational system. And for a while, we have the radiation bouncing off the asymptotic boundary and coming right back to the black hole. But at some point, we couple the bulk to a cold bath, which is to say we take we put transparent boundary conditions between these two systems and allow them to interact freely. And as a consequence of this, because this is cold, the black hole evaporates into the bath. And what we hope is that the evolution of the full system is unitary. This is what we would like to find. So this is how we force an ADS black hole to evaporate, even though it doesn't really want to. And now we ask, what do we see? So we compute quantum extremal surfaces in this evaporating ADS black hole. So we initially at early times, the quantum extremal surface is actually the empty set. What does that mean? It means that the area term here is 0. The area of the empty set is 0. And the von Neumann entropy is just the von Neumann entropy of an entire spatial slice of this space-time. So the von Neumann entropy of the boundary system is just the von Neumann entropy computed on this slice. And as the black hole evaporates into an external system, this von Neumann entropy grows. So, sorry, wrong slide. Now, what ends up happening where we deviate from Hawking's calculation is the following. Just after the black hole has evaporated half its mass, a new quantum extremal surface nucleates. This quantum extremal surface, which lies just inside of the event horizon, has a smaller generalized entropy than the empty set. What does that mean? Well, the empty set generalized entropy is given by the entropy on this complete slice. And the generalized entropy of this quantum extremal surface is given by its area over 4gh bar, plus the von Neumann entropy of quantum fields outside of it. And it might seem strange that the area over 4gh bar plus this von Neumann entropy can possibly compete with the entropy of the empty set, but it does. And so we find that it is advantageous that the generalized entropy of the quantum extremal surface here, that's just inside of the event horizon, is actually smaller than the generalized entropy of the empty set. And so just after the black hole has evaporated half its mass, we find that we need to take a different approach to computing the entropy than Hawking did. And of course, that is exactly the place where we would want to start deviating from Hawking's calculation, because Hawking's calculation continues to increase past the time when we've evaporated half the black hole, when Page's calculation shows that that's where we should start decreasing. So it turns out that this new quantum extremal surface actually has this decreasing entropy. And as we track its evolution for as long as we can until we get too close to the evaporation point, we find that the entropy indeed decreases exactly as predicted by Page. And so what have we done here? We've taken an area and we've taken a semi-classical, just weakly coupled quantum field theory, and we've done a computation that actually produces a unitary evolution for the entropy of Hawking radiation. Now, what happened here? What did we do? What is this magic? Well, we computed this quantity, where this state, rho out x, is exactly the state that would have given us the Hawking answer, a non-unitary answer, if we hadn't corrected it with this term from the quantum extremal surface. And this S von Neumann of the boundary computes the entropy of the radiation as predicted by quantum gravity. So what's interesting is that the only place where quantum gravity appeared is not in the calculation of this thing, but in its interpretation as a von Neumann entropy of the boundary state, von Neumann entropy of the radiation. This is the only place where we needed to use quantum gravity here, purely in interpretation. But that raises the question, okay, we have this great calculation, it gives us exactly the answer we want, unitarity. But what microscopic physics justifies the use of this prescription? What is it that we can, what are the words that we can say? We can attach this and say, this is why the quantum extremal surface prescription gives us unitarity. And to answer this question, let's ask ourselves, well, how would we generally justify the computation of an entropy? How do we generally compute an entropy? Well, one way of computing an entropy is we can do minus trace rho log rho, or we can use something called the replica trick. So this is the trick essentially is you introduce n copies of the system, and you do this trick over here. You take the limit as the number of copies goes to 1. And this is often a lot easier to calculate than minus trace rho log rho. So this is basically a different way of rewriting it, as long as this analytic continuation is unique. So this is not including gravity, just a general statement, but it's another way of doing the calculation. Now, what we can do is we can relate for in general, we can relate this trace of rho that appears over here. This is trace rho to the n. We can relate the trace of a density matrix for an unnormalized density matrix to the partition function. In ADS-CFT, it's a statement about equivalence of partition functions. So in general, in ADS-CFT, we can relate the partition function computing rho, or rho to the n, trace of rho or trace of rho to the n, to the so-called gravitational path integral. So let me just parse that statement in a second, but let me just say one word before, which is the partition function for this unnormalized state, rho to the n, can be computed using the standard path integral calculation in quantum field theory, but evaluated on n copies of the geometry on which the CFT lives. So we have n copies of the asymptotic boundary, essentially. And the gravitational path integral that computes this is this object here. What does that mean? Well, if this is an integral over all possible metrics that have a fixed boundary, and the integral is using the gravitational action here. So this is very similar to an ordinary path integral, except we're integrating over all metrics rather than fields. Now, what we can do usually, what we normally do is we use a saddle point approximation. So we just compute this using the saddle point approximation to the action for some classical solution to the Einstein equations. So what does all of this mean? The takeaway from this slide, with apologies, a lot of text, is that computing trace rho to the n in ADS-CFT translates into computing a quantity that requires spacetimes with n disconnected boundaries. So those of you who have seen a diagram of a wormhole, then that's something that connects two asymptotic boundaries. So here, this is a quantity that is computed from spacetimes with n disconnected boundaries. And remember, the reason that we want to compute trace rho to the n is because that's what appears in the calculation, in this calculation of the von Neumann entropy. And the reason we want to compute the von Neumann entropy is to justify this quantum extremal surface calculation. So we want to compute trace rho to the n using ADS-CFT, and we're going to do that using the gravitational path integral. Now, what does it mean that we're doing this? We're computing something from spacetimes that have n boundaries. Let's take a look what happens for n equals 2. You have two boundaries. That's two identical copies of the ADS boundary conditions at infinity. And for those who love technicalities, we're working in Euclidean signature here. So we're doing this gravitational path integral, or this here using some saddle point approximation, to compute trace rho to the n. So and here n equals 2, so trace rho squared. That means that we need to fill in this geometry. We need to solve for the geometry here with these two asymptotic boundaries. Now there actually are two saddles, two geometries that solve the equations and that we can actually write out. So here they are. There are two disconnected ones. So there's one disconnected geometry. So just you have these two boundaries, and each one of them, you just solve it separately. And there is also one which is a wormhole that connects the two. And the reason that the reason that we're doing all of this is to find some way of justifying the quantum extremal surface prescription. So some other way of calculating the same thing from top-down principles in ADS-CFT, like the equivalence of the partition functions. So what is the difference between these two? Well, this is the very standard thing where we just say, okay, so n copies of the boundary, you just have n copies of the bulk, and that's it. This one is unusual, and I'll say more about how unusual it is in a second. But what ends up happening, which is fascinating, is that at exactly the time when we expect this turnover in the page curve, there is a switchover from this to that. So if you're computing the von Neumann entropy, not using the quantum extremal surface prescription, but instead using this gravitational version of the replica trick, what you find is that using a saddle point approximation, for a while, this is the important geometry. And after, when you want to get the turnover to see unitarity of the entropy, to get the unitarity, you need to start including this wormhole. And in fact, you can justify the quantum extremal surface answer and the location of the quantum extremal surface using these wormholes here. So it appears that if we only use this, we would have seen something like Hawking's calculation. The entropy would have just continued to grow. But using this one, using this wormhole, we see that the entropy starts to decrease. Now, why is this important? Why am I telling you all this stuff about the gravitational path integral and wormholes and these technicalities about calculating the entropy? The reason I'm telling you this is because this has led to tremendous insights about what we need to be looking at in quantum gravity. Because the question that people immediately asked when they saw that these topologies, these connected wormholes need to contribute for us to get the unitary answer is, should they be included? Now, why would we be asking a question like that? And the answer is, these are connected so-called Euclidean wormholes. And what they result in are non-trivial correlations between these n boundaries. Why is that a problem? Well, these n boundaries correspond to n quantum field theories that are completely independent of one another. These are independent systems of just n identical copies. Everything should factorize between them. We shouldn't have correlations between these systems that are just n independent copies of the same system. So having these correlations means that we have this, well, the gravitational path integral on n copies of the boundary is not the same as the gravitational path integral raised to the power n. And in particular, the partition function on n copies of these is not the same as the partition function raised to the power n. And this does not seem possible in a single quantum theory. This does not seem possible we could have these n independent copies and not have any, and have correlations between them when they're supposed to be n independent copies. So what is going on here? We want to include these because these give us exactly the unitary answer that we want. They justify the quantum extremal surface calculation. They look exactly like what Page did, but they appear to be giving us a bit of a problem here because it doesn't seem possible that we should have this lack of factorization between n independent copies of the same system. So what's going on here? Well, the short answer is we don't know. One possibility that has been discussed is that the gravitational path integral actually computes an ensemble average, and that this is how that semiclassical gravity is actually an average over theories, which sounds crazy, but this is one thing that appears to be consistent with this result. Another possibility that maybe there are some fine-tuned non-perturbative corrections that somehow restore factorization. So this is where we are right now. And I would love to tell you that I'm going to solve this for you and tell you what the actual answer is, but I can only speculate. So I think one of the critical things that we have learned here is that the gravitational path integral is really smart. So we know, we're pretty sure these exotic topologies, these wormholes, these so-called replica wormholes, because they come into the replica trick, that they're legal, that we should include them, that it's not a coincidence that they give us unitarity. But it does raise the question of what exactly is the path integral calculating? And what I mean by that is the path integral is a black box, and it just spits out an answer. And an answer that knows about unitarity, but is not super consistent with a single quantum theory. And the question is it computing an average, maybe a disorder average, an ensemble average? Maybe it's approximating something. What is this thing actually calculating? Now, the only example that we have some understanding of is 2D dilaton gravity. And in that theory, it seems pretty clear that the path integral is doing a disorder average. But that suggests that the path integral, again, is doing an average over theories, over couplings. And that's not really consistent with the story that we have in higher dimensions. So what is it doing in higher dimensions? And in particular, what I would like to know is if we just wrote the path integral calculation and we say, what is the entropy, what is the state whose entropy this thing is calculating? How do we figure that out? What is the fine-grained microstate and the quantum gravity state whose entropy is being computed? Somehow the gravitational path integral know. How do we extract that information? Now, what I would argue is clear, is that we have pinned down a key ingredient in the resolution of the information paradox. this gravitational path integral, the path integral over all metrics that are consistent with some boundary geometry. This thing knows about unitarity. It's computing the right thing, but it's computing something strange. And we have to understand what this thing is computing and why it is so smart if we're going to make progress on the black hole information paradox. So current state of the information paradox, well, we haven't solved it. And I think some things that I would like to know, what entropy is the gravitational path integral actually calculating? Meaning, if I wanted to write down a minus trace rho log rho for the gravitational path integral in terms of quantum gravity language, what would I be writing down? How can I calculate this directly without going for the gravitational path integral? Also, what is an observer who is standing outside the black hole actually measuring? Now, if you're an observer, you can make arbitrarily accurate measurements. You have a bunch of beam splitters and mirrors and a really good quantum computer, and you fed all those results into your quantum computer. Do you see a pure state or a mixed state? If you're just standing outside the black hole, what do you see? Is the path integral doing some sort of an averaging, a disorder averaging, an average over coupling? What are the individual constituents that it is averaging over? Is the semiclassical limit of gravity just an approximate description of something like an ensemble? This is something that we maybe wouldn't have thought very much about, even though there have been some papers on that in the past. We may not have thought very much about this before we realized how important it is to include these contributions in the gravitational path integral in order to get closer to a resolution of the information paradox. And what are exactly the calculations, the corrections that Hawking failed to include? We can say, okay, well, there's the connected geometry and the disconnected geometry, and Hawking didn't include that one. But Hawking did a different kind of calculation. He essentially calculated minus trace rho log rho. And in that language, it is not clear where he went wrong. So I would like to know, where did he go wrong? What was he doing in the language of holographic entanglement entropy? What is the surface that computes the Hawking entropy? Those are all questions that we still have to answer. And I think answering any or all of them will certainly get us a lot further in getting closer to resolving the information paradox. And someday, understanding quantum gravity deep inside the black hole and in the pre-inflationary universe. So with that, I'm going to close there and thank you for your attention.
Thank you very much for this very stimulating colloquium. So let me ask if there are any questions. I want to remind everybody that Netta couldn't meet graduate students before, so we'll have a few questions, and then Shu-Yao will take over, and then the meeting will morph into a meeting with students. So after we are done with questions, I'll invite everybody who is not a graduate student to leave, and I'll put Shu-Yao in charge. Okay, so now questions.
Yeah, I had a question. You emphasized that once the black hole had evaporated to half of its mass, this is when the page curve would turn over.
Yeah.
Why half? Is that ad hoc?
Yeah, so this comes from something called essentially Page's theorem, which is about whether you have access to more than half the system. You can think of this in the language of quantum information. So if you have access to more than half the system, then essentially at that point you have the entropy has to start decreasing, because you can think of it as if you're essentially sliding the bar against the how much of the system you have, at some point you start to recover those degrees of freedom. So this is why the entropy has to start decreasing once you have access to more than half the system.
Thank you.
Thank you, Ken. Thank you very much, Netta, for this very nice talk, but most importantly, very important result. So a couple of questions. Following up on the Page's paper, didn't he have some understanding in it for that toy discrete system that he analyzed as to why the information wasn't lost through the infinite radiation process? And the second, and whether that can be whether that can give you some clue towards Hawking's calculation, what's wrong with it. And the second one would be in Euclidean gravity, path integral. Obviously, the Euclidean action is not bound below, and there are papers in the mid '80s in the context of solving cosmological constant that certain huge wormholes make it more and more negative, and there are issues related precisely to that. So I wonder if if any of that plays any role here.
So let me take the two questions in order. Oh gosh, I don't remember the first question now.
Page's simple toy model, if it gives you an
yes, thank you. Yeah. So I don't believe that any of Page's arguments are, any of Page's attempt at explaining what's happening are actually what we're seeing here. So it's possible that there is some roundabout way in which what he saw is related to what we're seeing. But I think because his approach was so different from ours, I think in order to cast it in that language, we probably will need to have a better understanding of the microscopics, because he was essentially focused on fine-grained entropies and fine-grained state of the system. So it's not impossible that he was onto something, but given that we've translated the problem into a different language, I think we may not be able to make contact with the way he framed it until we've essentially all but solved the problem. I may be wrong on this, it's a speculation. Maybe there is something that we can get out of it, but it's not obvious to me in the current language we're using how. So regarding your second question, sorry, can you remind me what it is?
Yeah, that was about the Euclidean path integral for gravity, which action is not bounded below. It's not positive semi-definite.
Yeah, great. So the Euclidean path integral, I hate to say this, but it's a little bit like a religion. It's not really well defined in gravity. We don't really know how to explain why it works, but the thing is that it works. It gives us it can count the microstates of black holes in the sense of giving us an answer to the entropy. This is Strominger-Vafa. They basically just said, okay, use the gravitational path integral. We don't know what it's doing, but it's computing an entropy. It's computing the correct entropy. So it's a little bit of a situation where when an answer doesn't make sense for the gravitational path integral, we sort of throw it out. And when it makes sense, we keep it. But we don't know why. It's not well defined, and we don't know why it works. And so certainly it's troubling that this thing has so many potential pathologies and at the same time seems to know a lot and give us a lot of information. And so I think that's one of the things that makes it very important for us to decipher what it actually is and find a way of actually defining it in a way that isn't confusing and doesn't have all of these pathological behaviors.
Thank you.
So Netta, I think I was next. So first of all, thanks very much. It's a great talk, really interesting result. And I just wanted to ask you, so first of all, I count myself as among the faithful in terms of the Euclidean path integral. So my question is, are there other things you can compute using these techniques that you've helped develop besides the page curve? So the page curve is having that shape is certainly necessary for unitarity, but are there other quantities? There are plenty of other things that would also have to happen. So
yes, I'm so glad you asked. So I've been really hoping someone would ask this, so thank you. So it's shameless self-promotion. So this past July, in a paper with Sebastian Fischetti and Alex Maloney, we calculated the free energy of JT gravity, the 2D dilaton gravity, at low temperatures. And we used the gravitational path integral. And what we found is that if you do not include the replica wormholes, if you just include disconnected topologies, then you have a pathological free energy in the sense that it's not monotonic with temperature. So you have a problem, you have a negative entropy somewhere. But if you include the replica wormholes, then you get very interesting behavior. And even though there was some non-trivial issues in the analytic continuation of the replica trick, we would hope that including these will actually resolve those pathologies. It seemed to make them better, but we couldn't actually do a complete resummation. So certainly there are other things you can calculate. And in fact, the free energy involves a completely different replica trick, but you still need to use the gravitational path integral to do it. And if you can complete the free energy calculation that we did, which would, I think with Clifford Johnson is writing a paper or has some results that suggest that you can, then you can actually see the signatures of these replica wormholes on essentially any observer you calculate from the generating functional in low temperature JT. And whether that happens in higher dimensions and what happens in higher dimensions, that's a different story.
There are other questions. I may have one. Actually, in any canonization process, we are talking about religion, right? When you make a saint, there is also a devil's advocate. So let me be the devil's advocate and saying, why don't you use canonical quantum gravity and canonical quantization where there, it seems that you don't need to include different topologies or topology changes because you have just an initial surface and then you evolve in time. Or if you want, maybe a better way to ask the question is, what does the canonical quantum gravity compute when we find, say, when we solve the Wheeler-DeWitt equation?
You're asking what does it, so I don't believe that canonical quantization is going to give us, so it's essentially, it would be a little bit like, unless you put in new ingredients, it would be a little bit like just doing this perturbative calculation. And we already know that without some new additional ingredients, we're not going to be getting something that evolves unitarily. So even though canonical quantization doesn't give you this additional topologies, in fact, I would see that more as as something that's problematic because we want these topologies to rescue unitarity for us. Now you can take a different perspective and say it's better for it because it doesn't raise all of these other complications that come with these different topologies. But then we have to we sort of back to square one as far as computing the page curve goes, because we don't have a justification of something like a quantum extremal surface prescription in that kind of scheme.
Thank you. I've seen that Kyle has a question.
Yeah, and Massimo, I think Shura raised his hand first, and then Sergey.
I don't know why I don't see the hands here.
It's under participants, but Shura is next. So go ahead.
Okay, so you have, okay, it's just good. So Kyle and Shura.
Okay, so who is first?
You are.
You go ahead, Shura.
Okay. So I have actually two small questions from someone from deeply outside the field. First of all, thank you for a very exciting talk, very interesting. I have two questions. One, about the bus. At some point, you said, oh, it's a problem if the thing evolves non-unitarily because universe is a closed system. And then you said, oh, we have a cold bus, but then you forgot about cold bus. So this created a disconnect in my mind. This is question number one. Question number two, you have replicas. Are you talking about replica symmetric solutions, or there is some spontaneous replica symmetry breaking?
Yeah, so I'm really glad you asked both questions because I have things to say about both of them that I didn't get to talk about in the talk. So first of all, regarding this, your discomfort with the coupling to the bath. So you're right that now once we've coupled this bulk system to the bath, now we could say the bulk system is now an open system and we don't expect it to evolve unitarily. The thing that we would like to evolve unitarily is the joint bulk bath system. So when I'm talking about unitary evolution in this setup, what I mean is unitary evolution of the union of the two. And that should be a closed system. So does that address question number one?
Well, to some extent, but then if this is a closed system, then in which sense bus is cold?
Then what, sorry?
Then what is the sense to say that bus is cold? You say
So we start out, so this is the dynamical process, right? We start out with some CFT in the ground state, and then we allow them to interact,
I see, okay, that's better.
Yeah. And so regarding your second question, so when we're talking about the replica trick, and really we should be talking about two replica tricks here. We have the replica trick for log Z, and then we also have the replica trick for the von Neumann entropy. So really we're doing a compounded replica trick. Now, the initial calculations were all done assuming replica symmetry. That said, in this work that I just advertised from this past summer, where we computed the free energy using the same method in a similar setup. And what we found was that the annealed free energy was pathological. The quenched free energy computed using replica symmetric saddles was a little bit better, but it was still a little bit pathological. And so we checked to see if the analytic continuation was unique, and it wasn't unique. And what we concluded from that is that there is in fact replica symmetry breaking, spontaneous replica symmetry breaking here, and that it looks a lot like a spin glass. Now, isn't actually a spin glass. It certainly looks very tantalizing. We weren't able to carry out the analysis because of various complications of the higher genus expansion in this gravitational theory. But we know that there are other ways of approaching this. So there was a paper recently by Clifford Johnson where he approached it from a somewhat different angle, and he also found a lot of similarities with spin glasses. So one possibility that we are considering is that low temperature gravity has a spin glass phase, which is a result of these replica wormholes, which I think in the condensed matter literature, they're just correlated replicas because these are not geometries, they're just correlations.
Thank you. It's very interesting.
I agree.
I am glad I asked.
Me too.
So I see, I don't know if that's the order, Sergey.
Sergey is next, yeah.
Thank you, Netta, for the great talk. So I was wondering whether these developments help to shed any light on de Sitter entropy. You measured inflationary universe, and so is there a similar story in that context?
So people have said some words about using quantum extremal surfaces in de Sitter to try to understand de Sitter entropy. Now, what I'm going to say is my personal opinion on that, and I think some people will disagree with me, but my perspective is that I don't know exactly how we should be applying the quantum extremal surface prescription to de Sitter. I think there are a number of complications. So one of the things that we tend to do is with this quantum extremal surface prescription is we have a homology constraint for the surface, something I didn't talk about, but the surface is homologous to the asymptotic boundary. If you have multiple boundaries, then it has to be homologous to different ones. Now de Sitter, we have time-like boundaries. What does it mean for a surface to be homologous to a time-like boundary? Do we impose the same kind of topological constraint? People who work on various approaches to DSCFT do attempt to do this, but I don't immediately see that there is a sort of a firm established connection here that we can use without any kind of concerns. Now, when it comes to asymptotically flat space, I think there's been more progress on this in particular on these developments where there have been some calculations that show that the quantum extremal surface prescription in asymptotically flat space, where I think it's more precise what we mean by that in that context, that it actually it also gives you a unitary page curve. So, but de Sitter, I would say there is the promise of something, but we certainly haven't solved it. We don't have a precise thing to say at this point, although I think some people will probably disagree with me on this.
Thank you.
So then it's time for Kyle, and I have other two hands raised by graduate students, but I remind graduate students that they will have actually time with Netta completely devoted to them. So I will let Kyle go first, and then I'll pass the baton to Shuya. Okay, Kyle, you can ask the question.
Okay. Yeah, thank you very much for the excellent talk. It was very interesting. Mine is a little bit of, I guess, maybe somewhat of a follow-up to Shura's question. I'm no expert on these things, but in terms of the replica trick, from what I've learned about it, it was one of these things that physicists sort of intuited and used quite a bit, but the kind of mathematical foundations were a little bit shaky and until like fairly recently. But I'm curious when you apply it in this kind of quantum mechanical or even like, quantum gravity context, I would guess that there's a lot more fine print in terms of the mathematical rigor. And I'm just curious if you can give any taste of like what possible loopholes there might be, and if those loopholes might be connected to the interpretation that you were referring to, like what are these replicas and do they mean anything?
Yeah, sure. So there's always the problem with taking the n goes to 1 limit of something that you're defining at integer n. Certainly we're talking about if there is the worry that it's not always clear that the analytic continuation is unique. And if it's not unique, how do you pick one? So that is certainly one potential problem. And in fact, as I was saying, with this replica trick for the free energy or degenerating functional, we definitely do see this exact problem come up, which is the analytic continuation is in fact not unique. Now, we expect that the correct analytic continuation should be picked out by some higher, some top-down thing in quantum gravity. So quantum gravity should pick out the correct analytic continuation. And so the question is, can we learn more about these replica wormholes by studying something else in quantum gravity that will tell us what the correct analytic continuation is? Now that's one thing that's related to replica symmetry breaking, which is something we often assume replica symmetry breaking. Now, there are a number of other subtleties on this. So again, the gravitational path integral is something that we use heavily in this gravitational interpretation of the replica trick. But the gravitational path integral, as was discussed earlier, is not actually well defined. So the Euclidean gravitational path integral is not actually well defined, and it has a number of issues with when do we interpret something that it gives us as something that makes sense, and when we say no, this is not well defined, and that's what's going on here. So I think if anything, we have a lot more. The replica trick on its own, I think, is so much better defined than the gravitational replica trick, which is what we use here. And nonetheless, because it seems to work, we tend to believe in it. But we should certainly look into the subtleties to see if those are if those shed any light on what's happening with the gravitational path integral and these replica wormholes.
Thank you.
Okay, so I think that we should thank again Netta for her talk, and then I will pass the control to Zhu Yao, and I will ask everybody who is not a graduate student to leave, so that that they can have the full field at their disposal. And thank you, Netta, for staying even longer.
My pleasure.
So I will thank you again. I hope to see you in person.
Indeed.
Then I'll give the good example by leaving.
Yeah. And the undergraduates can stay too, I guess, if there
undergraduates
are
can
any.
stay,
Yeah.
no.
Thank you.